All right, here we go. This actually is supposed to say 3.2 times 10 to the 12th. All right, so we're going to take that 3.2, and I need to move that decimal over how many positions? 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what do I stick in all those little zeros? Okay. 0, 0, 0, 0, 0. And to organize this, let's do our commas. There's our first comma, our second comma, our third comma, and our fourth comma. And there we go. Is that a massive number? Yeah. Millions, billions, trillions. So that's 3. No. 1,000. Yeah, so 3.2 trillion. Yeah. That's a big number. And to think our national debt is bigger than that. Okay? This is why we use scientific notation. Because it's a whole lot easier to write it as times 10 to the 12th than to write all these zeros out. Josh.
Just the 2 commas part of the 12 numbers. Like when you
The decimal starts right here. So you have to move it 12 decimals from that spot. Let's do a smaller one. 5.07. 1, 2, 3, 4. So stick in your zeros. Maybe we should rewrite this. 50, 700. Because when you have those swoops in there, Luke, sometimes it's distracting to try to see what the real number is. So if the exponent is a positive, what's the number going to be? Big, greater. And if the exponent's negative, what's the number going to be? Smaller. So then we move the other way. So let's go there. Now, when you're thinking, you got to think ahead a little bit here. So Ryan, as we do this, you got to think, oh, this is a small one. So start your 5.6 over to the right. Because you're going to have to move left, right? So 1, 2, 3, 4. So we have 0.00056. Does this make sense? Just how to move back and forth. All right, let's do the 8.3. How many positions do I move? 2. 1, 2. So I have 0.083. So converting from standard to decimal, back and forth between that and scientific notation. Let's look at the bottom. Putting things in order. Understanding what numbers are large, what numbers are small. All right? The easiest way to compare these numbers is to change them all to decimals. So here's where we're going to have to get our calculators out a little bit and make sure we're okay. Let's write 9 times 10 to the 7th as a decimal. Okay? How many positions do I have to move? 1, 2, 3, 4, 5, 6, 7. So that's 0.0000009. All right, there's our first one. Our second one. 0.00000. Let's see, I got to work backwards here. 1, 2, 3, 4, 5, 6, 7, 8. So I have 1, 2, 3, 4, 5, 6, 7, 8. Which of these two numbers is larger, which is smaller? Let's just start here. They're hard to compare. So what I do, Kyle, is I write them both with the same number of decimals. This has 7. This has 8. So I'm going to stick a 0 behind the 9 here, which is perfectly allowed. And now they both have 8 decimals. True? So now I'm comparing 90 versus 8. Which one's bigger? The 90. So if you write them with the same number of decimals, it's easy to compare them. Here we have something to the 6th. So 1, 2, 3, 4, 5, 6. So that's 0.00007. It only has 6 positions. My biggest one has 8 positions. So what do I want to do? Add on 2 zeros. So now they all have 8. So now what's the biggest one?
7.
Okay. Now, someone make a supposition or a guess for me. Something times 10 to the 10th. Would you say that's bigger than all of those or smaller than all of those?
Smaller.
It's going to be smaller. So which of these numbers is the largest? Okay, that's the largest. What's second largest? Okay, that's second. That's third. And that's fourth. How do you compare them? Write them all, Tara, with the same number of decimals. That's it. All right, let's look at B. A little bit easier. Which one has the smallest decimals? I got a 3 and I got a 3. Which of these two is smaller, do you think? Yeah, the 0.52. So let's start there. By the way, is that standard scientific notation? No. But it is a number. I'm going to move 3 spots, Grace. So 1, 2, 3. So I have 0.00052. So my standard right now is 5 decimals. Let's convert everything else to 5 decimals. 50.1, 1, 2, 3. That has 4 decimals. How do I make it have 5? Add a 0. 4.8, I'm moving that over 1. So 0.48. What do I need to add there? 3 zeros. And 56, 1, 2. I have 2 decimals. What do I need to add there? 3. So now we compare. They all have 5 decimals, and now we compare. What's the largest? Okay, that's the largest. So that's first. Second? 48. Third? This one? And fourth, this little 52. So the key to doing this is to make sure we write them all with the same number of decimal places. And if you need extras, you tack on zeros at the end. All right, pretty straightforward there, hopefully. Last idea, multiplying. And then writing in correct notation. What's 8 times 7? 56. Now, is that correct notation? So I need to write that 56 as 5.6, and here's the key idea. The number got smaller, so the exponent gets bigger. I'm going to put my finger right up here in the number line where the exponent is. What's bigger than negative 3? Negative 2. So the number got smaller, so the exponent gets bigger. So times 10 to the negative 2. Let's look at the second one. 0.2 times 3 is 0.6. Is that scientific notation? No. The 0.6 needs to become what? 6. The number's getting bigger, so the exponent gets smaller. So what does my exponent become? 10 to the first. Yes, sir.
So when you're increasing the number, you only move up and down by 1.
You move the exponent up and down by the number of decimal places you move. If that had been 560, we would have had to move it 2 down and 2 up. Make sense? So you move it the number of places that you had to move your decimal. In both of these examples, we only moved 1. That's a good idea. Maybe for next year, I'll throw a third example on, that said, here's your answer, 504 times 10 to the negative 6. That becomes 5.04. It moved down by 2, so the exponent should do what? Go up by 2. Does that answer your question, Josh? So a 2 to 2 ratio. It's a good point.
So you have to distribute twice 2 times.
The 10? No, that's the idea. You don't distribute. You only multiply by the front number. Excellent point. You don't distribute. You only multiply that 8 times the 7.